Welcome to this video on ceramics, composites, and functionally graded materials, focusing on the processing challenges of high-melt materials in additive manufacturing. This session is presented by Mr. Kunal Dewangan from the National Institute of Technology, Raipur. In this video, we will cover learning objectives including ceramic additive manufacturing, advanced composites, and functionally graded materials. We will examine processing methodologies for various materials and applications. Direct thermal processing of high-melt materials like ceramics presents significant challenges. High melting points often lead to thermal gradients, defect generation such as microcracking, and the need for complex indirect processing methods. We look at primary ceramic additive manufacturing modalities, lithography-based ceramic manufacturing, binder jetting, and direct ink writing. Each method offers unique advantages for structural and technical ceramics. Lithography-based ceramic manufacturing, or LCM, provides high density and precision. This process involves a building platform, photocurable slurry, and light exposure, followed by critical debinding stages to ensure structural integrity. Comparing binder jetting and direct ink writing. Binder jetting offers superior scalability, but can lead to lower green densities. Direct ink writing relies heavily on material rheology for success during extrusion. Technical ceramics like alumina and zirconia are vital for their hardness and toughness. Understanding their volumetric shrinkage during sintering is essential for manufacturing precise structural components. Silicon carbide and silicon nitride are at the forefront of high-temperature ceramics. Their mechanical performance depends on microstructural control and specific grain growth, making them suitable for demanding applications like medical implants. Polymer matrix composites vary by their architectural features. Continuous fiber methods offer high tensile strength, while chopped fiber methods, common in standard FDM, improve bulk stiffness and dimensional stability. Metal matrix composites can be fabricated via in-situ reaction synthesis or pre-alloyed powder blends. In-situ reactions often provide superior phase boundaries, while physical mixing simplifies feedstock preparation but risks material inconsistency. Cementitious and geopolymer additive manufacturing requires careful control of rheology. Balancing high pumpability with immediate buildability is the main challenge, with geopolymers serving as an eco-friendly alternative. Functionally graded materials enable compositional control by creating spatial transitions within a single component. Laser-directed energy deposition is key to this, effectively mitigating thermal stress between different materials. Continuous gradient deposition is superior to discrete joints. It helps prevent intermetallic phase formation and manages thermal expansion mismatches, which are common causes of delamination in layered structures. A notable case study is the use of litho-zirconia in medical applications. LCM technology allows for patient-specific dental and cranio-maxillofacial implants with high flexural strength and complex geometries. Thank you for joining this session on the frontiers of additive manufacturing. We hope this overview of ceramic and composite processing challenges has been informative. This video references several technical sources for its content, including research on ceramic processing, additive manufacturing workflows, and material science developments. Additional references utilized in this presentation cover metal matrix composites and advanced material characterization techniques. For more detailed information, please consult the cited journals and publications.